All right, our last little piece of this is how does n, the sample size, affect all this computation? So let's suppose that we have two experimenters. We have Eric and we have Michael. Eric has a sample size of 100 and has, out of the sample size 100, there are 80 successes. So the proportion is 0.80, 80 out of 100. So p hat is 0.80, q hat is 0.20. Eric is computing a 95% confidence interval. Suppose Michael is also computing a 95% confidence interval, but Michael has a sample of size 200 and a number of successes is 160. So p hat for Eric is 0.80, 80%. P hat for Michael is 0.80, 80%. So the question is, how do the sizes of the confidence intervals compare? Now, Eric is doing a 95% confidence interval. Michael is doing a 95% confidence interval. So Z alpha over 2 is the same for both of them. In both circumstances, as we can find from our table, the Z alpha over 2 is 1.96. Both of them have p hat estimate to be 0.80. Both of them have p hat estimate to be 0.80. Both of them have q hat is 0.20. Both of them have q hat is 0.20. So as we compute the confidence interval, p hat plus or minus z alpha over 2, then we have the square root of p hat times q hat all over n. That number is fixed or known. That number is given here to be 0.80. P is 0.80. Q is 0.20. That's the same for both Michael and Eric. The only thing that's different is the sample size. So Eric would say p hat, well, let's go ahead and put the number in. Eric would say p hat is 0.80 plus or minus 1.96 square root of p hat is given to be 0.80, q hat is 0.20, and n for Eric, n was 100. For Eric, so this is Eric, this is the computation. For Michael, same number, same number, same number, same number. This is the difference. This is going to be 200 for Michael. So Eric, we would have 0.80 plus or minus 1.96, and I'll compute 0.80 times 0.20 divide by 100, and then the square root of that number is 0.04. So multiply that by 1.96. And that is 0.0784. I'm going to leave all the decimals on so we can get a better comparison. So with a sample size 100, everything else equal, margin of error is 0.0784. Michael does the same computation, except Michael uses 200 here instead of 100. So Michael works out to be 80 plus or minus 1.96, but now this number is 0.8 times 0.2. This time it's divided by 200, and then take the square root of that, and that is 0.02828. I'm going to keep several decimals to get a better estimate. And so this is 0.80 plus or minus, multiply that, 1.96 times 0.02828. Our value is 0.05543 approximately. So what do we glean from this? We glean that for a sample of size 100, 7%, almost 8% margin of error. Sample of size 200, margin of error is 5.5%. Larger sample size, keeping everything else equal, larger sample size means smaller margin of error. Larger sample size means smaller margin of error. Smaller sample size means smaller margin of error. Keeping everything else equal, to increase the accuracy, to get larger accuracy, to make a smaller margin of error, you need a larger sample size. Large sample size, small margin of error. Small sample size, large margin of error.